Hi, my name is Mirza Charifian. In this video, I am going to tell you what exactly are strong and weak forms. We know that the behavior of physical systems is governed by partial differential equations along with boundary conditions. This set of equations is referred to as the strong form. However, in the finite element method, we don't solve the strong form directly. Instead, it is transformed into an equivalent integral form that requires less continuity from the solution. This is known as the weak form. Then we apply an admissible weight function and a trial solution, leading to the formulation of finite element equations. Although this process might seem a bit involved, it allows us to solve complex problems that would otherwise be intractable. In the rest of this video, we'll derive strong and weak forms for one-dimensional problems. Let's get started. Finite element method, part 6, strong and weak forms for one-dimensional problems. The goal here is to introduce strong and weak forms in the finite element method and its application to one-dimensional problems. As I mentioned, the behavior of physical systems can be described using partial differential equations or PDE and initial or boundary conditions. For one-dimensional systems, PDEs become ordinary differential equations or ODEs. The strong form for a problem consists of partial differential equations and the associated boundary conditions. However, in the finite element method, we use the weak form, which is an alternative integral formulation of the strong form. At the end, we need to apply the approximation functions to find the algebraic system of equations in the finite element method. Here you can see a path to develop the finite element equations. Now we want to derive the strong form for a one-dimensional structural system. For this purpose, we consider an elastic bar under attraction of T at x equals L and under axial distributed load or body force of B of x along the length of this bar. At x equals 0, there is a support, so displacement at this point is equal to 0 in x direction, and elastic modulus of this bar is considered to be E, and cross-sectional area can change along the length of this bar. The purpose is to derive the governing equation for this elastic bar. To achieve this, we actually consider an infinitesimal length at a distance of x. At section x, the internal force is N. At section x plus dx, internal force can change, and now it is nx plus dn. Along this length of bar, the applied external force is a body force B of x, and cross-sectional area is A of x. Now we could write equilibrium equation in x direction that will be nx plus dn plus bx times dx minus nx, because it is in opposite direction, all is equal to 0. Now we could eliminate n and minus n and then divided the rest by the x, and now we have this ordinary differential equation based on internal force. But in fact, we need an differential equation based on u, displacement. So for this purpose, we could use the definition of normal stress, which is n divided by a. So we could write n, internal force, is equal to a times sigma, and then we could use the definition of Hooke's law. Sigma is equal to E epsilon, and definition of normal strain, epsilon is du by dx. So instead of sigma, we could write E epsilon, and instead of epsilon, we could write du by dx. So internal force can be A times E times du by dx. Now substituting this expression for n into the previous derived differential equation results in this differential equation or governing equation for this axially loaded elastic bar, which is d divided by dx of a e dau by dx plus b of x is equal to 0 on uh, an interval x greater than 0 and less than L. To solve the achieved differential equation, the boundary conditions must be applied. The boundary conditions here are sigma is equal to t at the end of the bar, x is equal to L, and displacement is equal to 0 at the beginning of the bar, which is x is equal to 0. Or we could write instead of sigma e times du divided by dx at L is equal to t. This boundary condition is called a natural boundary condition, and the other boundary condition, which is u at 0 is equal to 0, this boundary condition is called essential boundary condition. Now the strong form is defined as the governing differential equation along with the boundary condition. A strong form for this one-dimensional problem can be written as d divided by dx of a e du divided by dx plus b is equal to 0 for x, a member of an open interval of 0 and L, and the boundary conditions are e times du divided by dx at L is equal to t, natural boundary condition, and the other boundary condition is uh, u at the beginning of the bar is equal to 0, which is an essential boundary condition. The solution of the strong form determines the displacement ux on the domain of the problem here along the length of the bar. However, in the finite element method, this is accomplished using the weak form and applying the approximation function. Now I want to derive weak form for one-dimensional structural system. But before that, it's worth to mention that in finite elements, the adaptation of the weak form enables us to use an approximate solution for the problem. However, the precision of the solution can be increased as needed by refining the mesh or utilizing higher order elements. So, to derive the weak form, the first step is multiplication of differential equation and natural boundary condition by an arbitrary function which is called weight function w of x, and then we need to integrate them on their domain. So this is the differential equation. I multiply this by w and then I integrate this from 0 to L on the domain of the problem along the length of the bar. It must be fulfilled for all w function. Also, I will do the same for boundary natural boundary condition. This is natural boundary condition. I multiply this by w and then I integrate this on its domain, which is the cross-sectional area at x is equal to L. So up to now, the differential equation and natural boundary condition have been fulfilled. But how about the essential boundary condition? In the finite element method, based on the displacement method or stiffness method, the essential boundary condition is directly met using the admissible trial solution. In fact, it is easy to construct a trial solution that could fulfill the essential boundary condition. In the next step, I want to decrease the derivative order of u and increase the derivative order of w, because if we refer to this equation, we could see that the derivative of u is has a order of 2, because 2 times we take a derivative of u, 1 time here and 1 time here. But if we refer to the w, the derivative order of w is 0. So I want in the next step to decrease the derivative order of u and increase the derivative order of w in order to have the same derivative order for w and u, because of 2 reasons. One, the trial solutions with lower derivative orders are easier to construct and guess, and the second reason is the same order of derivatives for the trial solution and weight functions results in the symmetric stiffness matrix, which is a desirable feature. Now, to decrease the derivative order of u and increase the derivative order of w, first of all, I write this integral as a two integral, the blue part and the black part, and then I applied the integration by parts to the blue part. For this purpose, I could multiply w by the integration of this part, which will be wae du dx from 0 to L, minus the integration of the derivative of w times ae du dx plus the rest. Then I could calculate this sentence one time at L and one time at 0. It will be wae du dx at x is equal to L minus wae du dx at x is equal to 0 plus the rest. And at this stage, we could apply the natural boundary condition. So we know that at x is equal to L, the traction is t. So instead of e du dx, we could write t. So we have this equation. In this equation, the derivative order of w and u are the same. Both of them have the first derivative order. Additionally, since the weight function w of x is arbitrary, it is selected to be equal to 0 where the essential boundary condition exists. For this problem, at x is equal to 0, we have the essential boundary condition, and we select to have a weight function is equal to 0. As a result, the second sentence in the previous equation is eliminated. So if we refer here to this equation and select a weight function is equal to 0 at x is equal to 0, where the essential boundary condition exists. So this sentence is eliminated and we only have the rest. And we could write the integration from 0 to L dw by dx times ae times du by dx is equal to integration from 0 to L wb plus wat at x is equal to L, where we have the natural boundary condition. For all arbitrary function or w function with w is equal to 0, where the essential boundary condition exists here at x is equal to 0. So a displacement function u of x that is sufficiently smooth and satisfies this equation is the solution of the problem. Finally, the weak form can be stated as find u of x among sufficiently smooth functions that fulfills u is equal to 0, where we have the essential boundary condition for this problem at x is equal to 0, such that this equation is fulfilled for all w or arbitrary weight function with w is equal to 0 at x is equal to 0, or we can say where we have the essential boundary condition. So this is the weak form, and if we compare this form for the problem with the strong form, we can see that in the strong form the derivative order of u is 2, but in the weak form the derivative order of u is 1. So in the weak form we could use the solution or the displacement function that requires less continuity comparing to the strong form. Also, we could mention some remarks. 1. Natural boundary condition is associated with the load or traction, and it is also called Newman condition as well. Since this condition or this type of condition comes naturally into the solution, as we see in the process of the solution, it is called natural boundary condition. Second remark, essential boundary condition is associated with the displacement, and it is also called Dirichlet condition. Since in the finite element method based on the stiffness approach, the displacements are the principal unknowns, the displacement boundary condition is essentially required to be met, and that's why it is called essential boundary condition and we apply it directly. Remark number 3. The admissible displacement functions must satisfy the essential boundary conditions and be smooth enough. These functions are called trial or candidate solutions. For the case under discussion, the sufficient smoothness means that the first order derivative of u of x must exist, requiring the C0 continuity. If we refer to the weak form, we can see that there is a first order derivative of u, so u functions must be at least C0 functions. Remark number 4. The admissible weight functions must become 0 on the essential boundary conditions and uh, must be smooth enough. For the case under discussion, the sufficient smoothness means that the first order derivative of u of w must exist, requiring the C0 continuity. So if we refer to the weak form again, we can see that there is a first order derivative of w, so w functions must be at least C0 functions. Remark number 5. The sufficiently smoothness of the trial solutions and weight functions is also required that these functions fulfill the integrability of the weak form, technically being a member of H1 space, which is a subspace of C0 functions. It means that not only U and W functions must be at least a C0 function, they need to be integrated in the weak form. So they need to be a member of H1 space. Also, we could restate the weak form in a more compact form by defining two sets of u and w. Sets of w is all functions of u of x such that u of x belongs to h1 and u of 0 is equal to 0. Set of w is all functions of w of x such that w of x belongs to h1 and w of 0 is equal to 0. So we could state weak form in a more compact form as I write here. Find u of x belongs to u such that these equations fulfilled for all w belongs to set of w. Now we want to solve an example, example 6.1. Apply the equations derived for the strong and weak forms to the one-dimensional structure below. Then use the given trial solution and weight function and determine the bar's displacement. In this example, we have a bar under distributed force of B0 times x. The cross-sectional area of this bar is constant along the length and it is equal to A, and elastic modulus of the material is E. We want to find the strong and weak form using the drive equation that we have found earlier. So just we need to apply the property related to this example into those equations. And after finding a strong form and a weak form specific to this problem, we could apply trial solution and weight function given by this example to find the final solution of this problem. It means finding the displacement of the bar. So for the solution, as I mentioned, first of all, I want to find a strong form. This is the strong form, the equation of the strong form we have obtained earlier. Just we need to apply cross-sectional area, elastic modulus, distributed force, and we need to adjust the natural and essential boundary conditions. So cross-sectional area is constant and is equal to A, and elastic modulus is constant again and is equal to E. So we could take them out of the derivation, and instead of B of x, we could apply B0x. So this is the equation for the strong form, the differential equation. AE d to the power of 2 of u divided by dx to the power of 2. The second derivative of u plus p0x equals 0 for any x belongs to the open interval of 0 and L. So for the natural boundary condition, we could refer to the bar and we could see that there is no traction at the end of the bar. X is equal to L. So we need just to apply 0, substituting instead of t. And essential boundary condition remains the same because at x equal to 0, there is a support and displacement is equal to 0. So this is the strong form for this problem. Second step is finding the weak form. And we want to use the weak form we have found earlier. This is the weak form statement. Find u of x among sufficiently smooth functions that fulfills u of 0 is equal to 0 such that this equation is fulfilled for all weight function of w with w of 0 is equal to 0. So we're considering b of x as b0 times x and traction is equal to 0 at the end of the bar. And now we can restate the weak form and tailor the weak form specific to our problem. Find u of x among sufficiently smooth functions that fulfills u of 0 is equal to 0 such that because a and e are constant, they can be taken out from the integration. So it will be a e times integration from 0 to L dw dx du dx equals b0 because b0 is a constant times integration from 0 to L x w dx for all functions of w with w of 0 is equal to 0. And this is the weak form specific to the bar we have in this problem. Third step is to finding the displacement function. The displacement function can be determined by applying the given trial solution and weight function to the weak form we have found here. Based on the weak form, we can write, if we refer to the weak form, we could see that u of 0 must be equal to 0. W of 0 must be equal to 0. Also, we need the first derivative of w and first derivative of u. So we could find alpha 0 and beta 0 using u of 0 is equal to 0 and w of 0 equal to 0. So if we apply this equation at x is equal to L, it results in alpha 0 is equal to 0. And if we use this equation at x is equal to 0, it means that 0 is equal to beta 0 plus beta 1 times 0. This sentence is 0, so beta 0 must be equal to 0. Up to now, the equation for u of x is equal to alpha 1 x, and for weight function is beta 1 x. Now we need the first derivative. If we take the first derivative of u and w, for u is equal to alpha 1 and for w is equal to beta 1. Now we want to actually apply these first derivative of u and w into the weak form. Now we want to substitute the trial solution, the weight function, and their derivative into the weak form to find the solution. So if we refer to this equation in the weak form, we could apply instead of dw dx beta 1, substituting du dx alpha 1, and instead of w we could use beta 1 x, and this will be the result. Now we could find this equation because beta 1 and alpha 1 are constant. They can be taken out from the integration, and this will be the result. And now we want to compute the integration from 0 to L dx and integration from 0 to L x2 dx. This integration will be x from 0 to L. It will be L, and this integration is x to the power of 3 over 3. From 0 to L, it becomes L to the power of 3 divided by L divided by 3. And then we could bring this side of equation to the left side and factor out beta 1. So it must be fulfilled for all functions of w. So the parentheses must be equal to 0, and if we find alpha 1, uh, it will be equal to beta 0 L to the power of 2 over 3ae, and substituting alpha 1 into the equation of u of x, we could find uh, displacement function for the bar u of x is equal to beta 0 times L to the power of 2 divided by 3ae times x. This is a linear equation for u of x, or displacement. It is approximate because we use the approximate function. Because the approximate function we have used are linear, and solution actually has been done on the entire length of the bar, but using higher order functions and or discretizing the domain by more elements will increase the accuracy. Now I want to find analytical exact solution and then compare the exact solution to the approximate solution I have found earlier. So for finding analytical exact solution, we could use solid mechanics equation. This is the bar under distributed force. First of all, I need to draw free body diagram and detach the bar from the support and apply the reaction force instead of the support. The reaction force is beta 0 L to the power of 2 over 2. We could integrate distributed force on the length of the bar to find this reaction. Then we need to find free body diagram for the length, for the x length of the bar. We consider a length uh, x length of the bar, and here is the reaction, and we apply external distributed force b0x, and on the internal section we need to apply n of x internal force, which will be equal to beta 0 L to the power of 2 divided by 2 minus beta 0 times x to the power of 2 over 2. We could find this internal force by writing the equilibrium equation in x direction, then to find the displacement function of the bar in any at any actually distance of this bar. We could use the definition of normal strain, which is epsilon of x is equal to first derivative of u displacement. So displacement will be the integration of normal strain on the length of the bar. Instead of the normal strain, we could use the definition of Hooke's law, and we could write sigma divided by E. And instead of normal strain, we could use the normal strain definition, which is equal to uh, normal internal force divided by cross-sectional area, which is A here. And now we could apply the equation for the internal force that we have found earlier. This is the equation. And now we could calculate this indefinite integration that will be this equation for u of x, or displacement of the bar at any x, which is beta 0 divided by 2ae times L2 x minus x3 divided by 3. This is the exact solution. Now I want to compare the approximate and exact solution for displacement and normal stress. This is the function for displacement we have found for approximate solution by finite element method. For finding normal stress, we need to use Hooke's law, which is sigma is equal to E epsilon, and instead of epsilon, we could use the definition of epsilon, which is the first derivative of u. So we need to take the first derivative of u and then multiply the result by elastic modulus E, and this is the result. Sigma of x is equal to b0 times L to the power of 2 over 3a, which is a constant function. It means that along the length of the bar, normal stress is constant, and it is equal to b0 L to the power of 2 by 3a. To find normal stress for exact solution, we need to use Hooke's law and definition of normal strain. So we need to take the first derivative of a displacement function, and this will be the result b0 over 2a times l to the power of 2 minus x to the power of 2. Now, for the sake of comparison, I have plotted the displacement for approximate and exact solution. The solid blue line is for approximate solution, and dash red line is for exact solution. As you can see here, the approximate solution is kind of close to the exact solution, considering that we use a linear approximation for trial solution. Also, I should mention that at the beginning of the bar, x is equal to 0 because we apply the uh, displacement boundary condition directly. The approximate and exact solution is exactly the same. But for stress, again, I have plotted approximate solution and exact solution. Approximate solution is illustrated by a solid blue line, and exact solution by dash blue line. As you can see here for stress, the difference is higher than what we have for displacement, and it is because the stress is not the main or principal unknown or a variable in finite element method based on the stiffness method. Now I want to explain general presentation for strong and weak forms. For this purpose, we need to define some parameters. One of them is n, which is outward unit normal on the boundary points. It is equal to 1 when its direction is aligned with the positive x direction. Otherwise, it is minus 1. It means that on this boundary point, which has the normal to the surface in the direction of the positive x direction, n is equal to 1. And on this boundary point, which has a normal to the surface in the opposite direction of the positive x direction, n is equal to minus 1. Also, we need to define another parameter, which is omega. Omega shows the domain of the problem. For this problem, if we consider the length of the bar is equal to L, omega means that x is from 0 to L. The domain of the problem is denoted by omega. Also, we define another parameter, which is gamma. Gamma shows the boundary point. Gamma u shows the boundary point related to the point where the displacement is known. U is equal to u bar, and gamma t is related to the boundary point where the traction is known. For example, here traction is equal to t. Either of the point could be gamma u and gamma t. So the strong form now could be restated as d dx of ae du dx plus p is equal to 0 in x belongs to omega, and ne du dx is equal to t on gamma t, natural boundary condition, and u is equal to u bar on gamma u. U bar could be 0 or could be any other amount. And weak form can be restated as here. Find u of x belongs to the set of u such that integration on omega dw dx ae du dx is equal to integration on omega wb plus wat on gamma t for all w belongs to the set of w. Also, we define complementary conditions, which is the union of gamma t and gamma u is equal to gamma, and the intersection of gamma t and gamma u is empty. It means that we, uh, we don't have any boundary point that none of the displacement or traction are known. Also, we don't have any boundary point that both of them are unknown or both of them are known. Also, we have the definition for the set of u and the set of w. The set of u is all functions of u such that u belongs to uh, h1 and u is equal to u bar on gamma u, and set of w is equal to all functions of w such that w of x belongs to h1 and w is equal to 0 on gamma u. Now we have an exercise for you. Use the weak form derived in example 6.1 and the trial solution and weight function below to determine the bar's displacement and compare the obtained solution to the exact solution. Here we have a bar that we had in example 6.1 and we want to apply this trial solution and weight function, which are the second order functions, to the weak form we derived in example 6.1 to find the displacement of this bar. At the end, I would like to mention that follow-up videos on the subject of finite element method will be posted. Thank you.